Thank you, Dr. Tati. Thank you, Dr. Tati, for inviting me. It's a pleasure. I'm happy to present at the research round. So, just an FYI, I'm in India right now, so it's 9:30 in the night. So, there's no Wi-Fi guarantee. So, I'm staying in a hotel. So, I before booking, I checked with them that everything should be okay. So far everything is fine. So, but just an FYI. So, I'm basically I grew up in India and then I studied basically in US, and actually I was in Canada as well for 2 years in University of Alberta. So it's always my pleasure to come and speak for for Canadians. So yeah, today I'm in actually beautiful state here in India in Himachal Pradesh, and it's so today I went for hiking, so you can see up there. So reminds me of Banff and Jessel Park. I don't know how many of you have been there. So beautiful Rockies, same thing in Himalayas here. So anyway, so without further ado, I'm going to talk about my ultrasound imaging research. This research started somewhere in 2017, around that time. It certainly some I just ran into someone, and then we started like how we can apply this ultrasound imaging into electrical stimulation, and from there I have three different projects that I'm going to talk about. So so first project I'm going to talk about, so that's my talk outline today. So first of all will be hybrid exoskeleton, which basically combines electrical stimulation and exoskeleton, and and then I'll move into more voluntary effort modeling for cable-driven exoskeleton, and then our most recent project is on tremor suppression using below motor threshold stimulation. So if you have to stop me anytime, just let me just raise or send me chat, or just let me know that you have a question. So you can interrupt anytime. So the hybrid skeleton project is mainly focused on people who have spinal cord injury, and mainly there we are working towards designing new control methods which can help them stand up and walk. And the primary thing is the electrical stimulation, and University of Toronto or KITE actually has, I don't know whether you need introduction on electrical stimulation. Many great people are over there who work on electrical stimulation. So basically, you know how electrical stimulation works. There are both implanted versions and there's a in non-invasive versions. I'm going to mainly talk about non-invasive electrical stimulation, in which these electrodes are usually placed over the skin and on applying electrical current. Basically, the motor neurons get activated, and then you can help someone like spinal cord injury, uh, you know, uh, actually get desired muscle contraction. So here's one individual who has spinal cord injury. This is something first time we tested on spinal cord injury electrical stimulation. And it was always amazing to see that how electrical stimulation can induce muscle contractions. It's all non-invasively. The moment even if there's no brain connections, signals not going to the muscles, but you can artificially induce these currents. So I'm hoping everybody knows about electrical stimulation. I don't have to talk too much about it. So I'm directly jump into how to use electrical stimulation for walking. So here's one commercial system, Parastep, that is available, and you can produce this coordinated movement using applying electrodes at multiple locations. So, for example, you can put electrodes in the quads and electrodes at the on the peroneal stimulation, and you can produce this coordinated movement. So there are reasons why I want to use electrical stimulation. Patients use their own muscles, so you can reanimate their paralyzed muscles, and there are a lot of therapeutic benefits to use electrical stimulation. So this is the first case when this FES was used for standing and for gait restoration. Um, so what I've been working for the last 10 years is how to control electrical stimulation. We derive some nonlinear control and adaptive control methods to control electrical stimulation, and there are many challenges. For example, the model itself is nonlinear. That model also changes every day based on how much you have exercised, or even if you have drank a lot of water. It is very finicky type of model. I mean, I would say like it's much easier to control an electric motor than controlling a muscle. So this is I've been focused on how to design better controllers, which I probably won't talk today, but I will mainly focus on the muscle fatigue, which is a major problem in control of electrical stimulation. How to compensate for electrical stimulation. For example, what is muscle fatigue? So muscle fatigue, as you know, you probably when you run marathon or something, or even you take a sprint, you probably get tired. Is a metabolic changes in your body, your heart, there's a metabolic fatigue. But here with fatigue, I mean is muscle fatigue, which is much more localized. It's like muscles do not generate enough power. But in case of external stimulation, like in FES, this fatigue is much more dramatic. For example, I stimulate someone with spinal cord injury, and let's say I want to hold on to certain leg angle, let's say 40 degrees, and the the actual angle, which is the when I stimulate, which is the actual limb angle, starts to drop right within 30 seconds. I mean, if I ask you to do it, probably most of the people who have no disability, they can hold their leg up like a leg extension for more than a minute or so. But this is kind of a problem, and I apply electrical stimulation, muscles fatigue very quickly. And the reason behind is like how you recruit these muscle fibers. So there are different type of muscle fibers, like the fibers that fatigue very slow, but they generate also much less force. On the other spectrum, there are muscle fibers that fatigue very fast, but they also produce a lot of strength. So it's like if you want to walk, probably you use muscle fibers that are slowly fatiguing, but if you want to sprint, probably use fast fatiguing muscles. So, but the brain does it in a very natural way and more physiological way. It knows exactly how to control these muscle fibers. But when I'm using electrical stimulation, this is much more challenging because I cannot choose what fiber types are being recruited. So what happens is in the end that when I sending these electrical current to the muscle, basically there is no much discrimination. Wherever the current goes, all the muscle fibers get recruited. And most likely, people who have spinal cord injury, they have more fast-fitting muscle fibers. This is because of the injury. Their whole muscle physiology or chemistry changes, and they tend to have more fast-fitting muscle fibers. So the muscle fatigue very fast. So the question we have been asking ourselves, like, how do we compensate? And there are many other areas which you can use for designing uh, to compensate for muscle fatigue. Maybe you can design better electrical stimulation profiles. You can do optimization of stimulation parameters. There are many things you can try, but we took a different approach in which we looked into how powered exoskeletons are being used in to restore standing and walking. And as you know, powered exoskeletons probably would never fatigue as long as they have a lasting battery. So here's a
last time also. Right, and tracking was really good, the last wasn't. I realized the game were the same with the right and that. So. They don't the exact same. Besides me.
so, so here's an individual with spinal cord injury, and we are using an indigo exoskeleton. It's a commercial exoskeleton, and we are basically we can produce the same sit up, sit to stand, and walking using exoskeleton. There are many advantages, as I said. The exoskeletons don't fatigue as long as it's basically limited by the capacity of the battery. So, so the idea is how do we compensate for muscle fatigue? And the approach we took was like, okay, can we combine electrical stimulation with powered exoskeleton? So there, as you know, if the muscle fatigue, then maybe we can switch to use of powered exoskeleton. If the muscle has recovered, we can start using electrical stimulation. So that is the idea behind a hybrid exoskeleton. And another advantages are also is like because your muscles are also producing torque. So maybe you can use smaller actuators on the side of powered exoskeletons. And this in the end may also use lesser power from the exoskeleton end. So some of our earlier studies on leg extension, we showed actually how adding electrical stimulation in a kind of an exoskeleton type of system has some benefits. For example, if I use FES, let's say at the bottom graph FES to produce leg extension, due to fatigue, I can hold on to the leg, let's say up to 30 seconds. Of course, when I use only electric motor, I can run as long as I can want. So there's a dramatic difference from 30 seconds, let's say, to 120 seconds. So, I mean, I could even go longer if I use electric motor. But look at the torque being used, it's 20 Newton meters to hold on to a certain angle. But when I combine electrical stimulation, there are two benefits. Well, first, I increase the length of certain muscle, desired muscle movement compared to FES from 30 seconds to 120. So that's a top graph over here. Okay. And also I can reduce the amount of torque needed from the electric motor. So from 20 Newton meters to 10. So that's the two benefits. So I can reduce the amount of torque needed from the exoskeleton and also increase the FES use from 30 seconds to 120. So that's the benefit. So we started looking into how do we control FES and exoskeleton together. Of course, there's other challenges like how do we optimize both of them, FES and exoskeleton. It's a redundancy problem. And in order to optimize, I also need to understand how the muscle fatigue. So, and it's a very easy way to model that muscle fatigue. So let's say we have person with spinal cord injury, we keep on stimulating, we can model how the muscle decays in force. So let's say there's a normalized force, I can fit certain function, and also let's say if I stop stimulation, and I also look at the recovery. So this whole dynamics can be explained as a first order fatigue dynamics. It's kind of a differential equation, and using some system identification, I can identify these fatigue constants and recovery constants. But again, this is based on someone's data. You need to look at that data before you actually implement in a control system. These, as the model is very finicky, you probably these model parameters might have to be re-identified maybe every day or so, or maybe after maybe 2-3 days or something. So is there a sensor that we can build that maybe can be used alongside this kind of fatigue dynamics, and try to understand how the fatigue is, changing the muscle force development or something, and maybe we can use in the control of an hybrid exoskeleton. So I was at Pittsburgh around in before 2017. I ran into Dr. Kankim. He works in ultrasound imaging, and this is how we started looking into ultrasound imaging. Initially I was interested in using EMG to understand how muscle fatigues, but when we tried using EMG, it has a lot of issues like stimulation artifacts. How to filter that out? So it became very, very difficult to tease out the fatigue dynamics using electromyography. So as I said, I ran into Dr. Kankim, and he was interested in using ultrasound imaging for muscle. And I explained, okay, I'm working on hybrid exoskeleton. Can we use this? So from there, we just started looking into it, and then we wrote a grant, and then it was funded. And we did some experiments based on this. Sorry, just give me 1 second. I have to keep some water. Yeah, let me know if you have any questions. And I'm not monitoring charts, my chat, so probably you have to speak up. So so why ultrasound imaging? What are its benefits? Well, one benefit is like, let's say if I want to look at the fatigue dynamics of certain muscle region, let's say your VI, which is vastus intermedius or the quadriceps, I can directly look at it from the using ultrasound transducer, and I can quantify any changes that happens due to this electrical stimulation. So here's one example of strain map. So let's say how it works. Basically, I can measure joint torque movement difference. How joint torque is developing or any changes in that. At the same time, I can also look at certain muscle region using ultrasound imaging, and I can quantify if there are any changes. So here, one of the ultrasound derived signal that we're looking at is strain. This is muscle strain. So I want to talk about muscle strain in my next slides. So how the strain is measured? So we send these ultrasound signals, and from there we can, form these B mode images. And using the speckle tracking algorithms, we can find within a region how much is the tissue displacement from frame to frame, from multiple frames, and then from there we can derive the strain. So it's like we can apply some differential filter and we can derive the strain. So in one of earlier experiments, let's say what we did is we have on the left, you see is a pre-fatigue state of the muscle. So let's say I simulate the muscle. Let's say the muscle generates 20 newtons. Okay. And then I let the muscle and I send in a lot of electrical stimulation, let's say, which we call fatigue protocol. So in the middle. So quickly, as I send electrical stimulation, muscle starts fatiguing. So it drops from, let's say, 40 to, let's say, 15. And then I test again this to monitor what is the state of the muscle. So after my fatigue protocol on the right, post fatigue, the muscle has now dropped from 20 newtons to 10. So that's the force response. So what we showed that this drop in the muscle force correlates very well with the ultrasound derived strain. So here you can think about if you have color, just as a very rudimentary way of saying this is basically a strain measure. So so we can quantify actually how much is the strain. But here, if you see there are color coded regions, that means there's a muscle is contracting, but as muscle is fatigued, basically the contractility of the muscle has changed, which we can capture using strain. So we in fact showed that that the decrease in muscle force correlates very well with the post maximum strain, but also the total area that you see, the area of that color region that you see, that also drops. So this is what we established in our initial studies, that ultrasound-based derived strain correlates very well with the FES-induced muscle fatigue. So of course, the next step we wanted to do is like, how do we take this, what we established using ultrasound imaging? Can we close the loop in a hybrid exoskeleton? So here we have electrical stimulation, and here we have an exoskeleton. How do they can talk to each other so that they can change their assistance levels? So, but this is challenging. So all the previous results I showed was offline. So all the results that we're producing took 2-3 hours of processing the images. So now when we're using exoskeleton, you need real-time feedback. So the good thing about processing the strain measures is that let's say if I'm looking at certain image, and I can divide this image region into multiple regions, and I can parallel process any strain measures in these regions independently. So which means I can use some GPUs, kind of some program, and if I can process these changes in each regions individually, I can make this faster. So we thought about we can accelerate this computation from 1,000 seconds to 1 second. So that was our goal, and hopefully we can close the loop. So with that, we did first experiment in which we had person sitting down, and we wanted to produce some leg extension. So here's our ultrasound probe in the middle, and we have electrical stimulation. The ultrasound system acquires the images. We send it to some GPU processor, and then it computes some strain. And we actually combined this strain measure from the ultrasound with the fatigue model that I introduced before. So why we still need fatigue model? Because it's still not possible to take ultrasound image to to be at to process at very fast rate. So we are controlling at, let's say, 500 hertz. It's still not possible to process the images at that fast rate. Maybe it's possible in the future, but at this time, at this moment, we were getting a ultrasound measure, let's say every 20 seconds or so. And so every 20 seconds, a strain measure comes in from ultrasound. Meanwhile, your control system is still looking at some fatigue model, which tells, okay, if there's this much of electrical stimulation, this is much has been the drop in the muscle force. And if there's an update from the ultrasound, it kind of updates that measurement. So it's kind of a hybrid kind of measurement. So you rely on fatigue model, and then you correct your model based on the ultrasound-based fatigue, feedback. And then we did something very simple. We use some kind of thresholding. So if the fatigue has reached certain threshold, we switch to exoskeleton, and if the muscle has recovered, we start using electrical stimulation again. So here's one experiment. So you can see there's an exoskeleton, there's a motor at the knee, and ultrasound applied directly on the quadriceps. And you will see when the electrical stimulation is applied, the muscle actually bulges. So this is very dramatic. I mean, you can clearly see the muscle getting stimulated. So I'm going to show you the results. So this is basically seated knee extension experiments, and we showed basically that we can track certain desired knee trajectory regardless of the state of the muscle is. So the main control objective is that the desired tracking should be achievable. Okay. We don't care like whether you're using electrical stimulation, we're using exoskeleton, and that's kind of running in the background without affecting the desired knee performance. So in the gray region, what you see is like, let's say if there's a fatigue, which is at the bottom, if that drops to certain levels, so there's an ultrasound measurement comes in, so that's shown in circles. So if there's an ultrasound measurement tells you, okay, you need to update, there's a change in the state of the muscle, change your fatigue model update, and that update happens to below threshold, let's say 0.6. That means turn off electrical stimulation. So here you can see the electrical stimulation, and this point is basically switched off because my fatigue has reached a certain state. And the exoskeleton, so this voltage here in the green is the motor. And the electric motor basically picks up, it sends in more exoskeleton assistance. So there's no change in the angle tracking. That's working perfectly. While in the background, the system is switching between FES and exoskeleton based on the state of the muscle. And that feedback is coming from ultrasound. So the moment the muscle recovers, so here's another ultrasound update. It tells you, okay, the muscle has recovered. Okay, start using electrical stimulation again. So that's the idea behind it. It's something very similar to a kind of hybrid car. You want to switch between gas, and you want to switch between battery power. So in the background, you don't care. You need the car to just keep going. And while in the background, system changes between gas and and the battery. So same thing here. You want to switch between FES and the exoskeleton without affecting the performance. And that's happening because of the ultrasound feedback. So just recently, this is a paper cylinder review at the it's a conditionally accepted. We showed this thing can be done in walking as well. So here we used a different algorithm. It's called model predictive control. So here this helps in basically both FES and exoskeleton are working in cooperation. So both are active. So we did multiple trials. A person walks, spinal energy walks for let's say 20 walking steps, then rest. We do it again. We do kind of 3 or 4 trials like this. And here's our walking setup. So this is our kind of a linear transducer that we use to provide feedback. So first we locate the muscle that we're looking at. So this is a muscle view. This is the cross-sectional view. So you can see the RF rector femoris and intermedius. And we see, okay, we are looking at the right muscle when it is contracting using stimulation, and then we rotate um, to get basically the axial view of the muscle. So once we identify the right location, then we wrap it. And then that's the basic cross-sectional view. So you can see the VI at the bottom that basically contracts. So this contractility over the time will change, and then that's what we try to quantify using strain. So we just recently, so ultrasound probe is basically, you can't see that, but it's in that wire under the polythene, which is wrapped, and there's another medical kind of a tape that holds the ultrasound transducer in its place. Basically we're getting this feedback from the exoskeleton, from the ultrasound to coordinate exoskeleton and FES together. So this testing was done only on the one side of the patient's leg, and only one quadriceps. So this is still, there's a lot of machinery here. So the mobility control itself takes computational power, and there's ultrasound. So we wanted, as a proof of concept, we showed it only on the one side of the leg. Of course, we want to scale it back. So here you will see some ultrasound changes. Post fatigue, you will see the color basically changes. The contractility has changed. So just like I showed you, like our goal is that we want to use FES or exoskeleton, and they can switch back, and how they work in the background should not affect the performance. So say, let's say here we want to produce stepping. That means your horizontal foot position and your vertical foot position relative to the ground is stable. And that means you are not hitting something or anything while you're using FES or exoskeleton. It should not affect their performance. So with mobility control in the background, both electrical stimulation and exoskeleton are changing while without affecting this relative foot placement. So you're producing stepping, and this should not be affected. So here's something, this figure is, I'll do my best to explain what's going on. So we have a fatigue index, which is the measurement from the fatigue, and we have normalized it. So on the x-axis, basically, you see the fatigue index, the signal coming from the ultrasound. So what if one means that muscle has not fatigued, and if it is lower value, that means muscle has fatigue. So basically what you need to see is like from the right to left. So these S1, S2 are basically patients, spinal cord injury 1, spinal cord injury 2, the 2 patients. And on the left columns are the FES, how much FES the controller is using. And on the right is how much exoskeleton assistance is being used. So ideally, this mobility control works cooperatively. So ideally, what we have shown is that if the muscle is fatigued, that means it goes from 1 to a lower value. The electrical stimulation should reduce, while the exoskeleton should pick up. So this is what we have shown. Like as ultrasound feedback is coming in, the control system automatically tries to lower the electrical stimulation value because muscle is fatiguing. So ideally, you don't want to send more current. You want to stimulate less while using more of exoskeleton. So that's what we are seeing. The exoskeleton assistance increases while decreasing the electrical stimulation intensity. So these are these are all compiled results from people with disability and 2 people with spinal cord injury. So if we are taking in total 10 gait cycles. So here's we're writing first gait cycle when the muscle is fresh, and by step number 10. So by step, this is cumulative. This is multiple trials. So by step number 10, we have seen that overall the electrical stimulation usage drops compared to step number 1. And on the right, the motor, you will see that compared to step number 1, the exoskeleton assistance increases. So this is because of the ultrasound feedback. And what we have shown actually also is that if I use model only, that means if there's no ultrasound feedback, it is not as sensitive to the muscle fatigue. So in fact, if I combine ultrasound, so this is model with ultrasound update. So US is ultrasound imaging. So if I'm using model and ultrasound together, the system becomes more sensitive to fatigue. So it actually senses there's more fatigue than what your model is predicting. So if I use only model, then you may not, you might be very off. And while if I use ultrasound, I'm actually much more correct. So what I'm not showing is like our ultrasound measurements are very close to the let's say dynamometer. If you know what dynamometer is, kind of a load cell measurements, which is actually force measurements. The measurements from ultrasound correlate very well with the dynamometer readings. So that's our benchmark. And if I use model ultrasound, which we are predicting, we're making system more sensitive to muscle fatigue, which is exactly what we want. We want you want your system to read this fatigue condition of your muscle much more accurately, so that we can coordinate this electrical stimulation usage much more better way. So this is what the results show here, that our model with ultrasound updates is much more sensitive. And because of that, you're using less electrical stimulation if I'm using ultrasound. If I use model, I tend to use more electrical stimulation. And same thing, likewise, if motor torque is likewise increased. So because my system has become more sensitive, my system is much more accurate. That means it is using less electrical stimulation, which ideally should be, and then use more of exoskeleton. Okay, so here I'm going to transition to another topic. So this is all about fatigue modeling. So now I'm going to talk about voluntary effort modeling. So in voluntary effort modeling, previous results were with person who has spinal cord injury. That means they may be completely paralyzed. Let's say person with who have ACL level A. But there are people in spinal cord injury who may have some residual effort. They may be able to walk, like for example, people who have incomplete spinal cord injury, or even people with multiple sclerosis or stroke. They still have some residual voluntary ability. So, as if you know about neurorehabilitation, the holy grail there is that how do we help these people recover again using what they call assist as needed control, which means they want to encourage the voluntary effort. So the more the person uses their own muscles, more effort they're applying, that means they will be able to recover much more faster, compared to a system in which the exoskeleton or electrical stimulation provide more assistance. So if we have to encourage people to use a more voluntary effort, we need to measure it. If I can measure it much more accurately, I can pass this information to an exoskeleton or electrical stimulation. So this is a project was funded by NSF Career Award. There we actually combine ultrasound with EMG. So here I will not talk about electrical stimulation. This is much more talking about assist as needed control using exoskeleton only. And here basically we show that we can in fact combine ultrasound with EMG signal. So and the combination is very simple. So let's say we have a muscle model, a hill-based muscle model. It's a kind of a physiological model, and this type of model has been very well established. And here the model usually takes inputs from the EMG, electromyography signal. So let's say there's an EMG signal coming from as you trying to walk, and this EMG signal is fed to some kind of a model. This is a hill-based model, and that model predicts the ankle torque, let's say, okay, or the ankle moment. What we showed that you can actually combine this to this input to this model can be augmented by adding ultrasound. So here we take ultrasound measurements of, let's say, the gastroc muscle. So here we're using muscle thickness. So here's your soleus muscle and the gastrocnemius muscles. We can use ultrasound images, and we can measure their muscle thickness and how this muscle thickness changes. And this could be, if I normalize it, this could be considered as a activation signal. So we came up with this framework. In this, the input to this muscle model is a weighted signal. Let's say this EMG is a signal coming from the EMG activation, EMG sensor. And I combine with ultrasound. And what the motivation there was, like, why do we want to combine EMG and ultrasound? So EMG itself is a kind of some neurological signal coming from the spinal cord. And that kind of represents a electrical aspect of the muscle force generation, while ultrasound captures the muscle contractility or a change in the muscle to say geometry as muscle is contracting. So we combine this electrical aspect and the mechanical aspect, and combined together, this we're hoping that this fusion of signals could be will be able to produce the prediction of the ankle torque much more accurately. So here's the model input. So we are capturing we had a person walking on a treadmill at different speeds. We started at, let's say 0.5 meters per second to up to 1.5 meters per second. And the model basically measures the EMG from the soleus muscles, all ankle muscles, EMG of the gastrocnemius, and we also measured muscle thickness, which is MT here, of the soleus and the gastrocnemius. So we combine all of them together. These are the model inputs, and send it to we weight them, we find certain a suitable allocation coefficient, and then we predict this voluntary effort. So this is multiple gait steps, and we tried different walking speeds, and we were able to predict not only joint angle, but also the joint moment. So our results actually show that the combining EMG with ultrasound produces the least root mean square error, which means it has the highest prediction accuracy in terms of predicting ankle moment. So you can see that, let's say if I have data coming from, let's say if I have someone walk at 0.5 meters per second, and then I collect all these EMGs and ultrasound, and then I feed to the model, and model predicts something. If I train using 0.5 meters per second, I still maintain that accuracy with EMG and ultrasound. It certainly deteriorates because I'm predicting someone who's walking 1.5 meters per second. So let's say now I train with 0.75 seconds, and this accuracy, 1.25 meters seconds, it's much more accurate. So if you train with the same speed and try to predict same speed, you will, of course, will get more accuracy, and the accuracy kind of drops. But we also show that what if we mix all this data, if we have data from all the speeds, and then you try to predict some other speed, you will get much more accuracy. And overall, still, the combined EMG and ultrasound model predicts much more accurately. So in fact, we showed that we can improve this accuracy from 10% to up to 28%, depending on what speed you're predicting. So this accuracy could be improved using combining ultrasound onto the EMG. So ultimately, the idea is that we want to combine this in assistance needed control. So you have a model that predicts how much is the voluntary effort from a user, and the exoskeleton will provide assistance only when needed. So if the person is doing good job, great. You don't have to provide any assistance. But if the person is lacking, okay, provide assistance. But what is the exact assistance? That's what the model that we have developed using ultrasound and EMG. So that's what they're predicting. So we have also developed a cable-driven exoskeleton. You can see the model takes both EMG and gastrocnemius as inputs, and it's producing basically retarded efficiency. So cable-driven is like it's attached to the hips, but it kind of provides ankle push-off. We basically showed here is that this is my torque prediction. So here's this red curves are the torque prediction, what is the human is producing in the ankle, and the torque assistance from the exoskeleton is much lesser. So here's the human is producing more torque, and the exoskeleton is producing much less, so which is good. At the same time, we're also tracking some actual trajectory. And here we basically there S1, S2, S3 are different scenarios. S1 is someone if there's no exoskeleton assistance, if there's exoskeleton is moving in its free mode, you cannot track much better. But if I turn on assistance using S2 scenario, in which there's only EMG-based assistance is there, your tracking accuracy improves, but also compared to ultrasound-based assistance, which is S3 scenario, you end up providing more assistance. So the S3 scenario, which is the ultrasound EMG combined scenario, the exoskeleton produces the least amount of resistance, which is good. So here, the human is producing much more effort. All right, so that's now coming to the final the leg of this talk, which is on tremor suppression using what we call efferent stimulation. So moving from lower limb to upper limb. So the tremor, if you're aware of, affects people essential tremor. There are more than 11 million people in US alone. It's a big problem. It's very difficult for them to write, use, do any daily kind of activity like writing, holding a cup. It becomes very, very difficult for them. So here's an example. So the moment I ask them to do some postural tasks like hold up a cup, the tremor sets in. And what we have seen recently is that if I stimulate the wrist muscles below motor threshold, which is they can still feel it, but the stimulation is not strong enough to produce muscle contraction, we can stop this tremor. Okay. So here's when stimulation is turned on, the tremor is basically it's much more suppressed. So our goal is in this project is to how to model tremor suppression, come up with a better dynamical model of tremor, and then come up with a better stimulation protocols or better stimulation profiles to suppress tremor. The current state of the art in this area uses electromyography or some accelerometers or called inertial measurement units as a sensor to provide feedback. The biggest issue with electromyography is that it is affected by stimulation artifacts. In my next slide, I'm going to show how that actually affects it. So usually the people who are using EMG as a sensor, they have these intermittent phases in which they stop the stimulation to look at what is tremor characteristics are. They measure the frequency, and then once the frequency is measured, they turn on the stimulation. So they will have to do this very, very frequently. Whenever they have to take the measurements, they stop the stimulation. So it's not continuous intervention. So we want continuous intervention without stopping the stimulation to take these measurements. So that's why we were very interested in using ultrasound imaging. It is not affected by stimulation artifacts, and as I showed you before in other applications, that it has a very high muscle specificity because I can directly visualize the muscle. So the only issue lacking here is ultrasound imaging is not that viewable yet, but I will talk about that as well. So here's an example why EMG is not good for using, designing any tremor suppression protocol. So here's a stimulation. I'm taking EMG measurements. The moment I turn on the stimulation, this top figure shows its artifacts everywhere. The signal becomes saturated. It's very difficult to filter out. There are signals processing algorithms which you can work it out. But here's one kind of trying to show you the drawback of using EMG. The moment stimulation is on, the signal becomes so much saturated with the stimulation artifact. It's very hard to measure anything regarding tremor. But if I use ultrasound, so here we showed that you can derive tissue displacement from using ultrasound. So here's no stimulation. I can still measure how much the tissue displacement is using ultrasound. And even I turn on stimulation, there is no stimulation artifact, doesn't affect ultrasound measurement. So you can take ultrasound, you can use ultrasound to measure tremor
characteristics without getting affected by stimulation artifacts. So that is the biggest advantage of using ultrasound imaging in tremor suppression control. So first thing we established, like, can we characterize tremor? For example, can we measure tremor frequency using ultrasounds? Is it as equally effective as other conventional sensors? So two conventional sensors are EMG and IMU. So here, okay, if I'm not using any stimulation, so certainly I can use EMG. So there's no stimulation. The idea was, is EMG, IMU, or ultrasound are the equivalent or not? So that's what exactly we actually tested on 11 patients. So this also includes persons with Parkinson's disease. So we had 5 Parkinson's disease patients and 5 people with essential tremor. And we showed that the ultrasound also measures, there's basically no statistical significant difference between if I use EMG or if I use ultrasound. So, or IMU, all are equally good sensors. So when there's no stimulation. So basically this established that I can use ultrasound as a sensor to measure tremor characteristic. The next thing we did in this tremor suppression is to find some personalized stimulation frequency. There are many other stimulation parameters that we haven't tested so far, but stimulation frequency was much more easier way to show this as a proof of concept. So we tried different stimulation frequencies. So we applied electrodes on all wrist muscles. So we have 3 electrode pairs. We for each patient here shown in T1, T5 up to T11, we try different stimulation frequency and see which stimulation frequency was much more effective. We identified for each individual which produced the most suppression. Once we identified it, we actually close the loop with ultrasound. The ultrasound sees when this tremor is present. If the tremor is present, it sends electrical stimulation, and if this tremor goes away, then it stops the stimulation. So this is great. So we tested this on 4 patients so far, 2 Parkinson's and 2 essential tremor. So on the top, you see the ultrasound derived tissue displacement, so showing these colored blocks here. So the moment this is, so here you will see basically your tremor in the gray. This is some normalized, let's say, tremor amplitude. So at the same time, we're taking ultrasound measurements. So let's say this is the purple here. There's the onset of tremor. This tells the controller to turn on the stimulation, and this switching signal goes from 1 to basically 2. So now the ultrasound has triggered the stimulation, and the moment the stimulation is turned on, this tremor basically is suppressed. Now the ultrasound at the same time, it's not affected by stimulation artifacts, so we can take measurements anytime without stopping the stimulation. But since the tremor has been suppressed, now we're going to turn off the stimulation, right? The same time, so we have shown this on multiple patients. So if the tremor has suppressed, we don't need stimulation. We can turn off the stimulation. If tremor comes back, for example, in T12 patient here, the 4th at the bottom here, the tremor, since it comes back, we turn the stimulation back on. So this is much more, you can on demand turn on the stimulation whenever the tremor is present, and you can turn it off when the tremor is not there. But the good thing is that ultrasound take these measurements regardless stimulation is present or is absent. It is not affected by the stimulation artifacts. So in fact, we showed that in one patient, we can basically achieve suppression up to 72%. But of course, there are some certain patients where the suppression is still not that effective. We were able to get suppression, but it was not that much. Maybe that's because the person with that this 20% maybe has very mild tremor itself. So there's much more room to suppress further. So of course, our next step in this area is like, how do we model the suppression? Maybe we can research into, are there any other stimulation parameters that we can optimize or personalize? So that's, how do we do that? That's our next step. But ultrasound will be the main thing that we will be able to use ultrasound to model this tremor behavior. integral to all of this that I had talked about, all the projects, is developing wearable ultrasound. So far, all our transducers have been, the conventional ultrasound transducers, which are, as you know, they are not flexible, they are not wearable. These are any ultrasound transducer that you've seen in a clinic, exactly at what we have used. But of course, if we have to make this successful, if you translate this, we want more flexible transducers. And if you are aware of ultrasound field, this field is rapidly changing. I mean, certainly we have ultrasound transducers that are the size of that can fit in your pocket, just like a stethoscope. So there's systems like Butterfly. There are other systems like Clarius. They're selling these very portable versions of ultrasound systems now. So what we are trying on in our lab, actually, we collaborate with Dr. Shani Chang at NC State. They're developing these flexible transducers. So these transducers are, the idea there is to make them flexible, but also reduce the number of transducers to reduce the computational cost. So here's a transducer which is used in a flexible it's flexible prototype. We're using basically only 16 elements right now compared to 128 in an ultrasound transducer. So much more easier way of looking at the muscle and reducing the computational cost. So of course you cannot create an image because we have reduced the number of sensors from 128 to only 16. But still you can use some machine learning approaches to study these basically signals that are coming into. So maybe there's a room to explore here. There's a lot of things, machine learning approaches can be used to learn the signals that are coming from directly from the muscle. So and of course reducing computational cost. We have also generated a flexible version, which is a 32 element flexible transducer. This can actually create from using this 32 element, you can actually make a B mode image. So we actually compare that with the Clarius, which is a commercial ultrasound transducer, again a very portable version of ultrasound transducer, and we compared our 32 element transducer with the Clarius system. So with both, we can of course create a B mode image. We actually showed it's not as good as quality as a commercial. So on the left, you see this figure is 32 element. The image is much more smaller, narrower, because we have lesser number of transducers compared to 128 channel, which is on the right. But still, you can identify, so you can clearly see some similar features that you can get from this wearable transducer. We in fact actually we were able to recreate tissue displacement using both wearable ultrasound array and Clarius. They are very close. There's some time synchronization issue just because of we were not able to synchronize the signals, but I think this is very, very well achievable. So with this, I'll stop, and this is the video I want to show regarding the tremor. I'm sorry. Oh, okay. I was just looking at chat. Okay. I will stop here. I know that we are closer to 1 hour and people may have to go. So I'll stop here if people have questions. So please go ahead. Uh, just want to thank my funders and basically, oh yeah. So basically presented 3 applications here for tremor, for our hybrid exoskeletons, and for modeling voluntary effort. My funders here and yeah, questions.
Wonderful. Thank you so much. What an engaging and interesting talk, and very interesting and exciting projects. I know some people had to leave because it just 1 o'clock, and quite a few people had meetings starting at 1. But if there are any questions, we if you are available to stay a few extra minutes, please, people in the audience, if you have any questions, you can raise your hands. Raise your hand in Zoom, or and we can unmute you, or you can type in your question in the Q&A box. And while people are doing that, maybe I can start with a quick question. So you showed lots of interesting results about ultrasound in the first study that you showed about using ultrasound for fatigue measurement and correlating the measurements with FES and so on. Would self-report work? Are people able to identify the fatigue in the specific muscles that are being stimulated? And if so, is it possible to use that to close the loop?
So, I'm sorry, I couldn't follow the question. So question was regarding a self-report. So self-report is on the user.
Yes. Like, do we need to automatically measure fatigue, or can we just have a little control that allows the user to control?
Yeah. So, yeah. Okay, I got it. Yeah, thank you. So the people who have complete paralysis, they will not be able to sense or feel stimulation either. They will not even do, I mean, basically sense if there are muscle changes as well. So if we have fatiguing, there are multiple things going on. If you have metabolic fatigue, so your brain is telling you to stop, but that's kind of a physical, more mental fatigue or whatever, physiological fatigue. But there's also fatigue that's happened at the muscle level when when you exercise, the lactic acid is produced. It's very hard to quantify that type of fatigue. And when we have people who have spinal cord injury, they will not be able to sense it. So with complete paralysis, they will not even have voluntary effort, so they will not be able to report. Even if somebody has residual effort, so there are 2 different mechanisms. I will say that the way stimulation works and the way people voluntarily produce force is different. When electrical stimulation is being used, to stimulate the force or the fibers that are being recruited are much more superficial. When you're using voluntary, it's more physiological. So I feel like the answer to that would be, it will be very hard to quantify using self-report. If I closer to answer that, if that makes sense.
Yeah, that makes sense. And I have another question, and people in the audience, please feel free to jump in if you have any questions in the Q&A or raise your hand. So in the FES stimulations, a lot of times the stimulations are very sudden, and even in your video, you can see the bulge appearing very drastically. Could that be a contributor to fatigue? Like if you're extending your knee, you don't suddenly your muscle doesn't go to full force. It's more gradual. Do you think a more gradual approach could reduce fatigue maybe?
Yeah, okay, got it. So I think the issue there is the muscle volume, the difference in muscle volume. So as I said, when you're using electrical stimulation, the fibers being recruited are much more superficial. So the fibers that we are closer to the electrodes, they are recruited. When you're using, that's why they bulge up.
Yeah.
But when you're doing voluntary, the muscle volume is higher, and more muscle fibers are being recruited, and much more, physiologically cycling through it. There's something called spatially distributed spatially distributed asynchronous stimulation, which is much more closer to a physiological way of recruiting. You basically cycle through different electrodes to reduce fatigue. So the idea would be if you can send the electrical current much more deeper, let's say if you use implanted, maybe if you stimulate, you use a neural cuff, maybe then you can recruit maybe more physiological muscle fibers, which are much more distributed in the whole muscle volume. You may not see that bulge. But because it's much more superficial, I feel like the current just goes to few muscle fibers and they just all work so hard.
Very good. Excellent. Thank you so much. I know it's quite a few minutes after 1 o'clock, and some people left because they had other meetings. Maybe if you're still able to stay a couple more minutes, there's an answer one of the questions from the audience. And this one is, thank you very much for your great talk. Could you please explain how you're measuring the strain from ultrasound? Are you utilizing shear wave elastography for a model of UF plus EMG, ultrasound plus EMG? What do you think about the presence of neuromuscular fatigue, which alters the relationship between EMG amplitude and force?
Yes, so great. So when I'm using measuring strain from ultrasound, shear wave elastography is another approach in which you use some kind of mechanical transducer to find the muscle changes. Our approach with strain is closer to elastography, but it is not shear wave elastography. If that answers your question. So in short, it is not exactly the same. We are in fact measuring the tissue displacement over muscle multiple image frames, and from there we are taking the derivative of the tissue displacement to find the strain changes. And this doesn't require any external transducer that creates a shear wave. So it is much better than shear wave because you do not need any mechanical transducer. So it's all one ultrasound probe. In the case of ultrasound EMG, that's your second question. What do you think about presence of neuromuscular fatigue? Yes, it is possible, but we haven't looked into it. Yes. So there's something maybe we can look into the future, or somebody else can look into the future. Yes.
Excellent. Great. Thank you again for a very engaging talk. Please join me in thanking our speaker one more time.
Sure. Thank you.
Yeah, thank you. Oh, yeah, I think people in the audience are also thanking. Thank you. Great talk.
Thank you so much for inviting it. It's fun. Yes. Great. Bye.